welcome everyone to the webinar. As Juliana said, my name is Patrick. I'll introduce myself in just 1 second, but we'll just go over the agenda for today's webinar. So firstly, the main part of the webinar is to review essentially what Whittle SIMO is and what it does as part of your Whittle portfolio. We're also then going to go over recent changes to simultaneous optimization. And one of the ones I want to focus on is the Capex optimization that's now inside of Whittle SIMO. At the very end of the presentation, I just want to discuss very briefly robust mine planning with Whittle SIMO and Milawa ISIGHT as sort of the next logical step beyond some of the concepts we're going to be discussing in this piece. And then, as Juliana said, we'll take some questions, some of them in the webinar, and other ones we'll get in touch with you afterwards. So as Juliana said, my name is Patrick. I'm a mining engineer based out of Montreal. Focus primarily on planning and scheduling, and do a bunch of work with our North American clients on implementations of software, training, and consulting with our software. I've been with Dassault Systems GEOVIA for over 6 years, and I've been using Whittle for most of that time. So at the beginning of the webinar, I just wanted to confirm with everyone where Whittle lies in sort of the strategic planning spectrum. So obviously when we're talking about Whittle, we're talking about a strategic level scheduling. So that's going to be more at the life of mine level schedule, analyzing bigger picture options for the entire project duration if we're at the very beginning, or maybe planning the next big expansion phase or the phasing for future pushbacks. When we move more into that medium or short-term scheduling, that's what we call more tactical scheduling, and that's going to be accomplished in the mineshed realm rather than the Whittle realm. Before getting into SIMO, I just wanted to confirm some basic Whittle sort of concepts, and obviously this is a bit of a generalization, but I feel it's still a good explanation of the core workflows inside of Whittle. So essentially there's 2 main phases to the Whittle process. We have our phase 1 of the pit shells, and we have phase 2 of strategic scheduling. And just note, this is obviously not a one-time left to right operation, that we're going to need to go back and forth between the 2 and sort of iterate and look at different options as we move from one to the other. But essentially in phase 1, that's really the primary phase where we're entering all our parameters, geotechnical, economic, costs, recoveries, setting up our systems to really, with the end goal of generating nested pit shells. So the end result we need from that phase really is an idea of what our ultimate or optimal final pit shell should be, as well as the phasing or pushbacks to get to that ultimate pit. Okay. So once we have those geometries from phase 1, we're going to look to put a strategic schedule together using those shells. So the idea is inside of Whittle, we're going to use the tools we have available to create a mining sequence, to create a schedule, which is going to result in obviously a mining, stockpiling, and processing sequence, physicals, year-by-year breakdown of what we're doing. And we'll talk about some of those outputs in a second. But obviously the end result is to have the schedule and any details we need out of it. And then we also need some measure of the how good that schedule is, and that's primarily done by the value of the schedule, which is normally measured by NPV. So the goal in this presentation is really to look at those different Whittle scheduling tools, and with the end goal, obviously, of raising the mine value to maybe push that project value a little higher. So just following up visually on those 2 phases, obviously the pit shell node, most people are pretty familiar with. We have our pit by pit graphs, we have our breakdown, our nested shells. Can take a look at each phase and do some examination, do some sensitivity, looking at it, is it operationally sound, using some of the other Whittle modules like mining width and things like that to make them operationally sound. But in the end, those form the geometric basis for our schedule. Okay. On the scheduling side, maybe a little less familiar for some users, but essentially, as we said, We're going to select our pushbacks. We're going to select our ultimate shell. We're going to define some operational parameters as well, such as mining mill capacity, material classes, and how we're going to exploit those different phases, some bench limits, maybe some mining directions, things like that, okay? But essentially the Whittle tool is then going to schedule out and produce a schedule. So what are we going to see in the schedule? Obviously the end products, obviously with, you know, customizable reports, you know, as I was saying, the most important one's probably year by year breakdown of the main physicals, strip ratio, input grade, stockpiling information, cash flow, things like that, okay? Obviously that could be numeric or graphical. Some more detailed breakdown on maybe the bench schedules. What are we taking out of each bench from which periods? And then sort of a graphical. So maybe coding some stuff back to the block model or end of period surfaces to see where we're at, to sort of understand the schedule visually. So understanding the schedule visually and numerically. But obviously probably the most important measure is obviously the value of the schedule, and that's going to come from the cash flow and result in a net present value. Okay. Before we get into the different scheduling tools, an important feature is obviously the ability to handle multiple pits. So quite rare now, most bigger projects, you have sort of several satellite pits feeding some kind of a shared resource. So maybe it's a shared mining fleet or a shared processing circuit. So obviously we could produce a schedule for each one individually and kind of stitch them together. But that's probably not going to be very optimal. We sort of need to handle them together. So having the multi-mine capability inside of Whittle, regardless of what scheduling algorithm we end up using, really important to get that combined schedule and to start understanding the interaction between the phases from different pits. Okay, so that's going to be pretty important and an important component when we talk about changes recently to SIMO. So as we said, inside of Whittle, we have a couple different options for how we're going to schedule the particular scenario we present to the scheduler. So this depends on sort of what our license profile has and what module we've added or acquired to our to the particular license we're using. So at the very basic level, with only the core modules in Whittle, essentially you're only going to be able to do a basic schedule. So what I mean by basic means we're going to be using the fixed lead option or the fixed lead algorithm. So that one, most people are probably pretty familiar with it, but just in case you're not, essentially what that's going to do is sort of a rigid, arbitrary, but you know, operationally sound and simple scheduling approach. So fixed lead essentially represents a certain lag between one phase to the next. So if I have, let's say, a 2-phase pit and I have a fixed lead of 4, what that means is we're going to exclusively mine in phase 1 until we've exposed the first 4 benches. And at that point, then we're going to start phase 2 and advance phase 1 and phase 2 evenly so that that 4 bench lag or lead, depending on which way you're looking at it, is always maintained. So obviously there's no optimization. We're not looking at what's available on those next benches, what we have sort of exposed. Regardless of what we have in the bottom of phase 1 and what we have at the top of phase 2, we're always going to make that transition after 4. Okay, so no optimization, just a simple scheduling technique. The medium level or intermediate level of optimization is probably familiar to most users as well, and that was sort of the standard in Whittle before advances in the optimization. So that module is called Milawa, or scheduling technique, and that brings an intermediate or a medium level of optimization. So what we're talking about really is, you know, trying to determine when that transition point should happen. And, you know, another way to explain is maybe the optimizing the sort of balance between the phases or sort of just the mining sequence. So what we're looking at is based on what we have on those benches, you know, particularly more in terms of tons, you know, do I have enough tons to fill the mill or not? What's available on those exposed benches? That's going to sort of determine when I make that transition and how much I mine out of each phase. So a big improvement on fixed lead, obviously. There's some intelligence coming into play where we're not arbitrarily determining when those phases start. But obviously there's still some things we're leaving on the table. So that's where we move to the more advanced and sort of the highest level of optimization inside of Whittle. And that module is going to be SIMO or SIMO Advanced SIMO. So for the next couple minutes, we're just gonna treat that as one option. I'm just gonna call it SIMO, and at the end we'll break down the difference between SIMO and Advanced SIMO. So for now, we'll just call it SIMO. And what that's gonna do, that's gonna do the highest level of optimization, where we're optimizing multiple components at the same time. So simultaneous optimization of the mining sequence, the cutoff grade, and stockpile optimization at the same time, okay? And the idea here is that's gonna get us a better schedule than Milawa for the same scenario. So if we're trying to improve our project value, there's a number of triggers that are gonna help us do that, okay? So the first one is more of a preparation step that's gonna allow the other tools to take over a little more. But one of the key ways to improve the NPV is gonna be a better control of material, particularly on the ore side, or a better classification, a little more precision on the different types of material. So the idea is here, if we can maintain a bit more definition of material and sort of categorize different types of material differently, we're going to be able to better optimize what we should be doing with those subclasses. So that's going to be called blend bins, and we'll see that in a second. Obviously, the next way to raise the NPV is going to be increase the grade, the mill feed grade, assuming the mill is already full, obviously. That's going to be the way to improve our NPV. So in order to do that, obviously, we're going to need to use cutoff grade and stockpile optimization in order to do that. And that's where having the better distinction of material from the blend bins is going to help. And lastly, obviously, finding the best mining sequence possible. Optimizing that is going to help get not only enough tons of ore and maintaining a good stripping ratio, best possible stripping ratio, but also raising that grade in conjunction with the cutoff grade and stockpile optimization. So those are the main levers we're going to be using to improve the NPV. And so we're just going to talk briefly about each one of those as it relates to SIMO. So an important building block of Whittle that we need to make sure we're clear on, regardless of the scheduling approach we use, whether it's fixed lead, Milawa, or SIMO, is the scheduling unit inside of Whittle. So Whittle's not a block-by-block scheduling tool. Whittle's scheduling unit for strategic level planning is what we call a panel. So the panel, as you can see here from the picture, is where essentially each pit shell meets the bench. That forms a block of material, and that's really the scheduling unit. That when I'm talking about sequencing of the mining here, in this case, I could take block A, then I could take block F, then maybe I'll go to B, then maybe I'll go to G or something like that. Okay, so that's the level of precision that we're talking about when we're talking about a mining sequence. Okay, as we can see here, though, obviously there's a lot of material in A. So how am I going to treat that material? Am I going to treat it as a homogeneous mass, or am I going to break it down? Okay. So the idea with SIMO is we're going to set up blend bins to essentially break down that panel material into specific groups of material based on the grade or the elements that are located in the blocks. Okay. So by having this better selectivity, then obviously we're better able to treat and make decisions on what we want to do for those individual bins of material. That maybe one bin I want to stockpile, one bin I want to send right to the process, okay? Whereas obviously I merge all those bins together and get one sort of averaged ore grade, then obviously I have to do something with that entire group. So when we're talking about stockpiling and cutoff grade optimization, there's not much that I can do because I've sort of merged everything together too quickly, okay? So the example, sort of visual example, is sort of on the right there with those pebbles, that within that panel, we have a lot of different types of material, and I don't want to treat it all the same. So I don't want to group it all up into one big group and then make a global decision. I want to be able to handle similar types of material based on grade in a different way, okay, to better optimize what I'm doing with the material. So that's what we call blend bins inside of SIMO. As you can see in this screenshot here, the setup is very simple, sort of like setting up stockpiles essentially, where we specify the grade, the grade restrictions or the grade boundaries for each bin, and those we can generate and then tweak based on the project. Okay. Once again, if I have a multi-element situation like I do in this case, I can determine, does each element contribute to whether it gets into the bin, and if both do, then obviously I have the choice: do I want an equivalent metal grade? Do I want to use each min and max? Okay. So obviously the distribution of bins I create is going to depend on the data, and obviously I can't overdo it or underdo it. So it's about sort of finding the best sort of bin setup to use will get me the best and operationally sound approach. With that distinction, obviously another big step to improve the NPV is going to perform some optimization on both cutoff grades and stockpiles. And obviously those goes hand in hand, okay? Because obviously if the goal, as we were talking about with SIMO, is to optimize the cutoff grade throughout the life of mine schedule. So generally speaking, we're going to try and raise the cutoff grade. If we have a good ore supply, then maybe we can process exclusively a higher grade and stockpile some more marginal material for later years to move forward the cash flows, okay? But obviously in order to do that, I need to effectively use the stockpile. So that's why as part of SIMO, we also have stockpile optimization, not just the cutoff grade optimization, okay? And that stockpile optimization is a big step in Whittle. Those of you who are familiar with the more traditional buffer stockpiles, you'll know that those are used really as a backup and sort of used arbitrarily, not arbitrarily, but used indiscriminately, we'll say, that it's not really checking, does sending to that stockpile actually improve the schedule or not. Once I set it up, it will be used to allow me to keep mining, okay? Now, normally that will give you a better result, but you could have situations where it won't. Inside of SIMO, the stockpile utilization is optimized, that we're only going to use it, as we'll see on the next slide, if it improves the cash flow, okay? So as we're saying they're optimized, only material that will be later processed is stockpiled. So that could have been a situation before, once again with a buffer stockpile, where you may have actually sent material to the stockpile because it was economic or above process minimum grade at the time, but due to time variable inputs, maybe when it was time to withdraw that material from the stockpile, it was no longer valuable, and essentially at the end of our Whittle schedule, we had a balance in the stockpile, which obviously we don't want. So essentially, you can see there that Whittle SIMO is not really looking at a single period for the stockpiling and cutoff grade optimization. We're looking at the entire strategy for the life of mine. So we're only going to send that material to the stockpile if we can eventually recover it. And as we said, we're only going to send it to the stockpile if it actually improves the cash flow of the project. Otherwise, we're not going to do that. Okay. So I'm just going to point out that in this webinar, we really want to highlight the important concepts. If you're looking for more technical detailing on the linear programming of how the stockpiling or the cutoff grade optimization or the algorithm in general works, there's a very good white paper that goes into the mathematical details that's available on our site, or you can contact us and we can send that to you if you're interested in the more technical details behind the mathematics. Last component obviously is to optimize the mining sequence. And so we sort of have three things we're managing all at the same time. We're managing the mining sequence, we're managing the cutoff grade, we're managing the stockpiling, okay? So one of the big benefits to SIMO is that we're not optimizing these things in a silo, okay? The name SIMO comes from simultaneous. So we're actually optimizing these components simultaneously, that we're not locking in one before moving to the next one. And this is going to lead to some synergies between the factors, okay? So how does this work inside of SIMO practically? We're going to be doing optimization through iteration. So what I mean by that is we're actually not going to set a specific mining sequence. We're actually going to run a multitude of scenarios with random potential mining sequences. So we're essentially, the computer is going to try different mining sequences, and each sequence we're going to optimize the cutoff grade and the stockpile, okay? And we're going to track the NPV of that particular run, okay? So we're going to run a multitude of runs and we're going to keep tracking the NPV. Okay? Question obviously then is, when do we stop? So SIMO is going to stop when one of two things happen, okay? When either the maximum number of runs I've specified is eclipsed, and then we've said to stop. The other thing it may do is if we've converged within an acceptable tolerance. So what I mean is the solutions have started to big grouping at the very top, and we'll see that in the next one. We can assume that we've hit a global maximum. So I'll show you an example set up on the next slide here. When I'm running a SIMO schedule, I have to set up what we call the run control. So essentially, this is determining how many runs, how many iterations of the mining sequence do I want to try. So you can see in this case, I said your minimum start point is 150. So you have to do 150 different runs, okay? And that's what the computer will process. Maximum will be 200. So once you've done 200, then the node will be complete. The question is, I don't want to have to do those last 50 runs unless I really need to. So what we're going to do, you can see here, is I set up a tolerance on the best solutions. So in this case, if once I've run 150, what the computer is going to do is we're going to look at the top 10 solutions by NPV. If those top 10 are within 0.2%, then we're going to assume we've converged on the best solution, and I'm not going to waste time doing extra processing that I don't really need to, that I'm comfortable that I've hit the top solution. Okay. So that's sort of a different concept than we've seen in more traditional fixed lead or Milawa schedules. So this is probably the most important slide of the webinar, where we sort of summarize everything. On the right-hand side, you can see the different components that we're trying to manage. Okay, and on the left-hand side, we see the NPV. So as we're saying, we could optimize one and then move to the next component and optimize it. But by doing that, we're missing out on the simultaneous nature. So we can see the added bump in the purple where the sum of its parts is greater than the individual components, okay? Because we have that extra synergy by not locking in, by not optimizing each one in a vacuum, okay? And that extra component could be very important. That could push us between a no-go and a go for a project financing or an expansion or whatever we're examining with the strategic schedule. So that's probably the most important slide that I want you to take away from the webinar. And obviously the end goal, we said, was to improve the value of the schedule. So this is a particular example where in this case we have we've sort of, based on the different mining sequence and strategy, we obviously have different year-by-year physicals, and we've been able to move some of that cash flow forward, and in this case, producing a 12% increase. So there are some white papers and some case studies on the technology. Obviously, there's no set amount. Generally, a good correlation is the variability of the deposit. So if you have a very homogeneous deposit, then obviously optimizing the mining sequence and in cutoff grade and stockpiling considerations don't really come into play too much, because whether I dig here or dig there, the material is basically the same. So when I process it here in year 1 or year 5, once again, doesn't matter either. So it's not going to make a huge difference. Whereas if I have high grade variability and material variability, then the optimizer has flexibility and can sort of improve the timing of when that material goes through the system. So in terms of the interface, that's an important consideration, because obviously if we have a newer technology, okay, there may be a benefit, but is it very different than I'm used to working in Whittle? And that's what the really good thing about SIMO is, that essentially we're just using a better algorithm, but my workflow remains the same. So in the next couple slides, we're just going to show the interface a bit. If I was running a schedule, users would be pretty comfortable with adding a new schedule graph underneath the operational scenario, as you see at the top there, instead of adding sort of the Milawa or fixed lead schedule option. Essentially, there's a new schedule option at the bottom called simultaneous optimization. Okay. As we can see here, easy setup schedule, because it's except for a couple components, it's the same setup as you would have for a traditional Whittle schedule. So you can see in the bottom left, we have the pushback definition. So in this case, this would be a multi-mine situation where I have mine 1, which has 4 pushbacks, and mine 2, which has only 2 pushbacks. And we're obviously building a combined schedule that optimizes the contribution of both mines to the shared process, we'll say. Okay. As we said, one of the big differences is that run control. So that's where we set up the number of times Whittle's running. And for SIMO, because it is more of a 360 view, that we're not analyzing a period in a vacuum, we need to understand its impact on the whole schedule. I need to tell Whittle how long that schedule is. So what's nice about that is I'm not required to analyze the entire life of mine. I can put in that I just want to look at the first 10 periods and study that in a vacuum, okay? With traditional Whittle scheduling, obviously the schedule runs until there's no material left in the pit shell. So in terms of the interface, very similar to the traditional Whittle interface. You can see the blend bins, as I said, that setup is quite similar to the stockpiles. And then the stockpiling is obviously the same setup where we define the entry to the stockpile, we define rehandling costs, all the traditional components that you define with a stockpile. Okay. Everything else about the Whittle SIMO interface is the same. So on the output side, you'll have your output table, you'll have your definition to define what gets displayed in there, and you'll have your graphing along with all your traditional exports. The only difference on the output side is actually they're specific to SIMO. There's automatically an Excel workbook created called the SIMO report, which contains about 50 or so different pre-generated reports that vary in level of detail and what they're analyzing. So you can just see from the list, there's a few summary ones, which are sort of more larger picture year-by-year physicals. And then it can go down into very detailed material type reports, the material flow added to the stockpile, removed from the stockpile, etc. That's a very detailed year-by-year breakdown of each type of material as it moves throughout the system. So those are automatically created when I run a SIMO node, and I have all that information there. So that saves me from doing a bunch of work in the definition to then see it in the output, that I have this Excel report pre-generated basically for that scenario, okay? So I think I have another screenshot just showing some example. This would be more of a summary one where we have a year-by-year breakdown on the mining side, on the mill side, and on the selling side in this case. Whereas you can see at the top left here, more detailed one where I can see the material moving from blend bin to stockpile and then beyond in a more detailed breakdown. And you can see on the right-hand side just the sheer list of number of different reports that are automatically created and I automatically have access to when I run the SIMO, when I run a SIMO schedule. So I just want to talk briefly about some changes, some major changes that have happened recently inside of SIMO. And the big one is that Whittle 4.7 Advanced SIMO, but there's also a big new change in 4.7.1, which introduces Capex optimization, which is something that our clients were very interested in. So I said earlier we wanted to discuss the difference between SIMO and SIMO Advanced. And what's confusing to some users is that it's the same core functionality or algorithm, that the optimization algorithms and techniques are identical between the two. What Advanced SIMO unlocks for me is that it undoes some system limitations that we had with the base SIMO module. So the biggest and the most important one is that Advanced SIMO allows me to handle those multi-mine scenarios, okay? So when I have those multiple mines feeding into the same schedule and I want to optimize both together, that was something we couldn't do with base SIMO. So the Advanced SIMO was really important for most of our customers who have more complex projects where they really want that higher level of optimization because it's such a complex where I have multiple mines, each with multiple pushbacks feeding potentially a complex processing stream setup with a variety of stockpiles. That's really where they wanted that highest level of optimization, that it was sort of a single pit that SIMO would produce greater value as well, but most projects are more complex these days. So that was sort of a real important advancement to have Advanced SIMO, the tool that can now handle multiple mines. As I said, the other big change to SIMO recently was the ability to do Capex optimization. So what I mean by Capex optimization was, we can see here in a traditional Whittle prior to Capex optimization, when I'm running a SIMO schedule or a normal schedule, I'm going to get a result at the specific scenario I propose. So in this case, we're talking about, let's say, a mining limit. I might get a schedule. I'll get a schedule at 16 million tons. But the question is, if I'm at an early stage of project evaluation and there's still flexibility, should I use 16 million tons as my yearly mining capacity, or should I go for a larger fleet? Okay. So what the user would have to do is essentially manually try these different capital levels and obviously the capacity that goes along with it. Okay, so that could take some time. So the idea is inside of SIMO, they introduced the ability to do that iterations for you on the fly as I optimize my schedule, okay? So essentially what I have to set up is essentially the relationship, a linear relationship between capital and CapEx. So obviously in some cases, let's say use a plant for an example, it's maybe not a perfectly linear relationship, that there may be step changes that, you know, with a linear relationship, it may tell me the optimal mill size is 22.6 million tons. Obviously, when I'm sizing a plant or a fleet, there's probably steps that I can only do a 20 or 25, but it gives me a good breakdown for where that optimal level is, and then I'll adjust that based on what's practical, okay? So here's a simple example here where we set up a 60 million ton base case situation where we run the schedule with the CapEx required to meet that 60 million tons, and we achieve a certain NPV. The question is, why 60? Would 40 be better? Would 80 be better? I'm gonna have to try different scenarios, okay, to see, does the added cost of that 60 million, that extra capacity, is that paid back by greater cash flows, okay? So I would have to try that manually, and we'll see how this can now be done directly inside of SIMO automatically. So some of the parameters they did in this example is they said the fleet had to be replaced every 5 years. So every 5 years, we'd reanalyze where that capacity level should be. So it's not that I have to just specify it once at the very beginning. I could do that. In this case, just to show you the complexity, have that decision of where that capital level and capacity level should be every 5 years. The other thing is at this stage of analysis, you might not even know what that linear relationship is. So to add a ton of capacity, is it an extra $1? Is it an extra $1.50? Is it an extra $2? So you could try each one, and obviously each one's going to produce a different result. Yeah? So as a simple example, when we run it with a $1 per ton linear relationship between cost and CapEx, they determine that for the first, the system's automatically able to run through iterations, and we're able to determine that the optimal mining capacity for this scenario should be 54 for the first 5 years, then down to 48 for the next 5 years, and then down to 18. Okay, that the 60 was pretty close, but not quite on, and we want sort of a variable scaling of the project. If, you know, with our 5-year rule, we said that was doable. Okay, 1.5, obviously it's a different relationship, and so the optimal CapEx and capacity level is obviously different. So higher CapEx, but the greater capacity to get through the material pays for it. More at the 75 level, and then when I moved up to 2, it was basically up to my limit of 100 million tons that I thought would be feasible. So obviously a higher CapEx cost, an additional 218 million in this case, but the NPV was greater than my initial 60 million ton. So really the idea of optimizing and determining those CapEx levels inside the schedule without having to iterate manually outside the schedule. So that was an interesting piece for our clients. So that's the main points I wanted to cover with ISIGHT, with SIMO. I just wanted to spend a brief moment just putting sort of the next logical step in your head about where you go beyond SIMO. So just want to talk briefly about strategic planning using SIMO ISIGHT in conjunction with Whittle. So I like this slide. This sort of breaks down what we've been able to accomplish so far with SIMO. That for a particular scenario, in this case I'll call it scenario X, we have certain inputs, you know, metal price, recovery, costs, etc. Some things like that. Those are going to generate our pit shells, and we have additional inputs that come in at that stage in terms of the decision making, that I want this to be my optimal shell, I want this to be my pushbacks. So we push all those inputs together into our strategic scheduling box, and at that stage, as we've seen today, we have a decision for what optimizer I want to use. Do I want to use the Milawa tool? And as we've shown in this one, that the superior tool would be SIMO, where I'm looking at the scheduling, stockpiling, cutoff grade optimization, and all that stuff, okay, simultaneously. So at the end of that process, we can say we've optimized scenario X. But the question is, are there better inputs or different inputs I could have used that would produce an even better schedule? Okay. So that's where ISIGHT, which is a simulation tool, comes in, which allows us to automatically iterate through hundreds or thousands of Whittle runs, essentially. Okay, so it sort of sets up as an automatic loop that the user is going to run and then sort of walk away from as Whittle runs hundreds or thousands of times. So as you can see, it's sort of there. The idea, just the visual idea, is instead of just trying one scenario, we're going to try hundreds or thousands of scenarios, both on the sort of input side, but also on my sort of pitch shell level, and pass each one through to the strategic scheduling of SIMO. And that way we can compare all the different results and all the knowledge. So it's an optimization and understanding of the inputs to produce a potentially an even more optimal solution. And the key component is also robust, okay? Because obviously a lot of the components could be quite variable. And the question is, how risky is the solution? You know, picking the highest value schedule may not really be the most appropriate selection, because if any one parameter changes slightly, that schedule could perform very badly. So it's not just about having the highest value, but also being a stable or robust schedule. So having that knowledge and that ability to make decisions and react to changes is a big component of having those thousands of run rather than just the one. So the idea is also to eliminate the risk on the user end, that if I'm manually running different scenarios, I may, you know, do about 10, we'll say, okay? The success of my schedule then is going to depend on two factors: my experience in knowing which 10 to try, and a certain degree of luck. Did I correctly understand the dynamics of the project in terms of which shells to pick or something like that? Whereas obviously if we're running 500 or 1,000 runs, that element of risk is taken out, that I'm going to see all the possible solutions and then be able to make a better and more informed decision. So just to visually understand that concept of risk, some people like to display the solution set as sort of a surface, if we want to think of it that way. So it's not just about picking the highest value necessarily on the left, because we can see in this particular data set, that solution is very unstable. That a small change in any of my inputs, let's say metal price, mining cost, recovery, etc., is going to really hurt the project value. So what I may actually do is look for a more robust solution that's still very optimal, that's still very high in terms of value or whatever the key KPI I'm tracking, but you can see there's a little plateau there. So a change in any of the components doesn't really, the schedule is still valid, the value is still there, the scenario still makes sense, okay? So as I said, I just wanted to briefly do that component, that SIMO is optimizing a particular scenario. The question beyond that is, well, is that the best possible scenario to use, okay? And as I said, there is an existing webinar on this, and I believe there'll be another one in the future. And there's some good material from real case studies where we've applied this, particularly out of our Chilean office. So that's something I'd recommend getting in touch with us, or just contact us and we can put you in touch with some of that material. Some very interesting projects they've worked on this, the combination of Whittle and the Simulia ISIGHT simulation tool. So just some of those ideas of those different scenarios that they were able to try. What should the final pit be? Well, you know, what shells should I select? Then once I have the shells, well, how should I mine those phases in terms of directionality? There's a mining direction usually as part of the schedule. So where should I start? Starting point in the phase, and where should I mine? Okay. And the idea is we're going to run up those different scenarios to look at the strategic sequences, what produces best value. And as we saw at the very end in sort of step 5, okay, we have the different values, but then we also have the variability. How do these schedules react to changing inputs? And by inputs, I mean more on the fixed inputs. So cost, recoveries, price, things like that. That I obviously a higher price would produce a better schedule, but we're talking about things that I have no control over. How does the schedule react to changes in those inputs? In choosing a schedule that's right, because obviously at a strategic level of plan, we're looking at 20, 30-year mine life. Obviously all these parameters are going to change, and how does my schedule react to those changes? This approach will allow me to control that better and be able to react to those changes better as well. So that's essentially the presentation. I'm gonna just look through and take a couple questions. We're a bit tight for time, so if I don't get to the questions, we are going to get back to you by email. So I see a question about the practicality of SIMO And that's an important point. As we're talking about, obviously the operational constraints are very important. And that's really where the cell selection comes in. When we're talking about ramping consideration, it's an important point. But just note that that's sort of the idea behind any of the mining, the sequencing approaches, that the shells I present to it must be operationally sound. So if we have, if I presented shells that are not operationally sound, and then produce a certain, let's say, very high NPV from SIMO, then obviously, yes, that's a very high number, but it's unusable because I could never actually achieve that. So understanding the relationship between the phasing is very important, and even during the scheduling. So when I'm doing the scheduling inside of SIMO or inside of Milawa or any of the scheduling, there's certain restrictions I can put on in terms of the maximum lead between the different phases, the maximum number of benches. So those are all operational constraints. So I agree with the question that Whittle, if left on its own, regardless of what scheduling algorithm you use, is going to just do whatever makes the most money, whether it's operationally sound or not. So regardless of the algorithm being used, I need to put on the appropriate level of constraints, operational constraints, to make sure the schedule is feasible. But as I said, there are those constraints that you can turn on, whether it's a Milawa schedule or whether it's a SIMO schedule. Let's take one more here. I have another question about pseudo flow. So is pseudo flow is not really tied to SIMO. So pseudo flow is another sort of term that's relatively new to the Whittle space. So what pseudo flow is, that's an alternate to the Lurch-Grossman algorithm. So if we think back to my initial slide with the breakdown of the two different phases to the Whittle process, we had, sorry, just give me 1 second. We had the pit shell phase and strategic scheduling side. So SIMO lies in that phase 2, pseudo flow lies in phase 1. So that's when we're generating the pit shells, we're using the LG algorithm in the past. Pseudo flow is a new mathematical algorithm that is greatly more efficient and much faster at running the creation of those pit shells. So regardless of whether you use LG or pseudo flow, those shells are then passed to SIMO. So not a direct tie, but the problem is LG does not perform very well with large block models. So it would take, with such a time constraint and such a long process to generate those shells, that it really limited the amount of time you could spend doing the strategic scheduling with SIMO or with Milawa. So in other words, not really directly correlated, but an important new addition to Whittle to be able to allow you to generate those fast pit shells. So when you're doing your pit shells, you're gonna have a toggle. You can choose between LG algorithm or Lurch-Grossman, depending on which one you want to use. Okay, so that's, we're out of time, so I'm gonna have to leave it there, but there's a couple questions I'll get to offline, and I'll send you an email or give you a call and answer those for you. Just to wrap up, we just wanted to go over a couple of next items that are coming down the pipeline. Just note that we recorded this session, so it's going to be available online, so you can always go back and look at it again in our eSeminar section. And always try and keep up to date with the new products, tips and tricks and things we're discussing. So you can do that at any of the social media platforms, Twitter, Facebook, LinkedIn, or our blog, where we post a lot of interesting blog posts. And just to note, the next webinar is going to be Enabling Zero Distance with Social Collaboration, which will be on August 8th. So look out for the invitation or advertising on our social media pages. So thank you for attending. As I said, if you have any other questions, you can give us a contact, either the general contact or your local services team or myself. And as I said, if we didn't get to all the questions, we'll get in touch with you to answer those for you. And so yeah, that's all for me. Thanks very much for attending.